for you to please give a warm ShmooCon welcome to IanFoster, who says DNS is still lame.
Thank you for that. Does this work? Sounds good. All right. Hey, everyone. I'm Ian. All right. So a little bit about myself. I am way too interested in DNS and TLS. One of my projects is DNS Coffee, where I basically archive all of the DNS root zones every day and diff them and do large analysis on them. The work I'm talking to you about today is a little spin out of some of that. I've also done some stuff with TLS certificates, CertGraph, and Bygone SSL in the past. My current job is a red team lead at Snapchat, although this is not why I'm here. This is just, I'm talking only about work I've done on my own. And I go by Landrod Online. So for this talk, I'm going to talk about what DNS lame delegation is, what a DNS dependency tree is. I'll give some examples, and then I'll demo a tool that I've been working on. One thing that I am not doing is I am not covering how DNS works. I'm assuming you all know this, although it is more complicated than most people assume. This is a wonderful info comic that kind of explains how that works. I know most of you probably can't read it here. That's fine. It's made by Julie Evans. I highly recommend you look at it. It's a great summary. But for those of you who can see it, the part in these boxes are the parts I'm actually going to be talking about. It's what happens between your recursive resolver, like your ISP's name server, Quad 8, Quad 1, and authoritative name servers. So in that case, this diagram here, the DNS client, this is not you. This is the ISP's recursive resolver. In order for them to know what response they need to give you, the client, they start asking, like the root DNS servers look at a response of a delegate DNS record. In this example here for, say, example.com, it'll forward them to com's authoritative name servers. They'll then forward you to example.com's name servers. They'll then say, if you're asking for an IPv6, sorry, IPv6 address like a Quad A record, it'll respond with that. A recursive resolver will keep following this chain of NSs until it receives an authoritative response. So now I'm going to define lame delegations. Put simply, a lame delegation in DNS is one where a name server has delegated control of a domain, but the name server in question does not have an authoritative answer for that record. So in this example here, I say two, I'm not sure you guys can read this, kind of a little bit small, but the two different NS sets for example.org. One of them is ns.example.org. If later someone changes the NS records to be, say, ns.foo.com, but the ns.foo.com name servers have no idea about example.org or how to respond to it, that's considered a lame delegation. So going back to this example, instead of having example.org's name servers in the bottom right, it's another name server, has no idea, and it's like step 6 where it responds with the answer. It will respond with like an NX domain or a timeout. In this case, the domain name would fail to resolve. You'd have unhappy users. However, you can have partially lame delegations. So like many other DNS issues, they can be partially hidden. So in many cases, your domain name might continue to work normally, but a misconfiguration providers or their providers could allow stuff to still have an issue. So in this example, again, of example.org, it has one of the correct name servers and an incorrect one. The correct one will return an IP address. The incorrect one will either respond NX domain or maybe a timeout if nothing's listening. And users will still get the correct IP address. It still appears to work just fine, but this is still technically a lame delegation and can lead to problems that I'll talk about in a bit. So DNS dependencies. You start off with like the root, then you have the org name servers, and then individual name servers. And you see here I have the groups of each of the name servers that are responsible for this, for each zone and that are authoritative. For things to work successfully, only one of the name servers in each of these categories needs to actually respond correctly. This is like why DNS works so well. There's lots of redundancy built into the system. Going a little further, a given domain name, like example.org, depends on its own name servers, as you see here. But each of these name servers is actually just another domain name. And each of those domain names have their own name servers. And they also have TLDs, and TLDs have their own name servers. And this keeps going. So, and for some cases, that dependency of a name server having a domain name that has a name server, et cetera, can recurse many times, leaving a single domain name with upwards of 50 dependencies. Each of these can be a potential independent failure point, and it only takes one weak link in this to weaken or potentially break the chain. So if we wanted to enumerate some of those, here I'm only actually looking at what all the potential dependencies for, say, the actual DNS root, not looking at the org zone or example.org in this. You have your various name servers, like rootservers.net, which depends upon the net zone, which depends upon gtld-servers.net, which depends upon a domain name in the com zone, which of course depends on .com. And you also have a circular dependency here. This is what your recursive resolver will either do for you or may not. I'll talk about that in a moment. But no DNS client ever needs to actually do this. But let's go a little further. What happens if you want to do this exact same thing, but also map out .org and example.org? And a little warning, this is going to look a little bit crazy. And this is not how most recursive resolvers work. It's a huge mess. It took a while to make this graph, and I tried to make it as organized as possible. I don't think it's actually possible. So the reason why you don't need to do all this, or you and most recursive resolvers, is glue records exist that can short circuit a lot of this logic. And the root zone files will help you skip looking at, say, TLDs or name servers IP addresses that exist in other zones. Those are mostly there to help break circular dependencies, but they also help short circuit a lot of this other logic too. The glue records in the root name servers are non-authoritative, so some name servers might still query a lot past them, but it does still make stuff a lot faster and get rid of this redundancy problem. However, this does point out, though, that if there is a problem somewhere else in this giant mess here, that could still have an effect. It could be 2, 3, or more degrees away from the actual, say, domain name you have in question, and that can still have an impact. So partially lame delegation somewhere else here, even though there's so much redundancy, can be hidden, and things can continue to look like they're working fine. But if, say, name server started responding inappropriately, it could start to have effects on the rest of the system. So I've been talking about an authoritative name server, and not everyone might know what that is. So that is basically an authoritative name server is one that has the ultimate authority answer instantaneous question. You can easily see this by using the dig tool and querying a name server, and if it has the AA flag set, if you guys can see this right here, this is an example of the authoritative bit set. So here, for example, I'm querying for ShmooCon.org using Google's Quad 8. That's just a random recursive resolver on the internet. It has the right answer, but it does not have the authoritative bit set, as you can see underlined here. However, if I query one of ShmooCon's actual authoritative name servers, I do get the authoritative bit set. So if any recursive resolver, including, like, say, Google's in this example, once it reaches this, it will return the answer to the client and not query any further. So now I want to very quickly to show how one could manually do this recursiveness. Actually, go through each step that a recursive resolver does so you can see where the potential lookups could go wrong. Just starting off, you just ask for the root servers. You get a list of them here by querying for dot. And let's say again we want to resolve ShmooCon.org. It's a great website. You should all check it out. Query one of the roots from the prior step. You ask for, say, an A record for ShmooCon.org, and you'll get the org name servers over here. And then, of course, now we have the TLD org servers. We're just going to ask them for the A record for ShmooCon.org, but they don't know either. So they'll refer us to the 2 ShmooCon name servers. In this case, this is the end of the NS referral chain, but sometimes this can go many, many more times steps. And the last step here is ask the Shmoo NS server for an A record. We get an IP address, and also note the authoritative bit is now set in this answer. And when we have an IP address, we can view the website. Everything works great. In this example, we picked the first name server each time, but what happens if we chose another one? So in this example here, we chose the crush.shmoo.org, .com. If we were to choose the other one, Archimedes, it actually times out right now. This is a lame delegation. So Archimedes.shmoo.com appears to be unused. Whoever can control that IP address that it resolves to can actually perform a partial takeover right now of ShmooCon.org and all other domain names that Archimedes.shmoo.com name server uses. So what can we do about this? The best type of thing we can do is basically, there's no automatic way to detect this type of stuff other than just continually querying and enumerating all of these dependencies and see if anything is wrong. Best to try and make it automatic. If the problem is upstream of you, like in that giant DNS mess I showed earlier, that's outside of your control. There's not much you can do. You can notify the network operators, and hopefully they'll be receptive and work on fixing that. Another thing is to try to set your DNS infrastructure to as few external dependencies as possible. So, like ShmooCon, don't have a ton of chains of name servers. And there's some TLDs, for example, have more dependencies and more not. Some, like cloud providers, will have more or not. Try and map them out and see what the various temperatures and want as small dependency tree as possible. So I worked on a tool called Broken DNS. I worked on this while working for Google, but I got open source when I left. And it enumerates the entire DNS dependency tree, tests all possible routes. So unlike a normal recursive resolver that only tests, once it gets a valid answer via one path, it says it's good and returns, it tests every possible permutation a different route could possibly take, and will notify you if there's any errors. Even though there's no caching like a normal recursive name server will do, it is still incredibly fast. It removes all redundant queries that I might need to do to resolve stuff within the same tree. It can learn lame delegations, unexpected names, answers in name servers. You can identify other hidden problems, which I'll show a few of examples, and also authoritative name servers providing different responses. There's 2 different authoritative name servers, or claiming to be authoritative, showing different responses. So now I will try to show a quick demo of this. All right, so. So I was going to run this very briefly on ShmooCon.org. As shown earlier, when we do this manually, one of the name servers timed out, so this will actually, there is retry logic in here in case there happens to be a network failure or whatnot. It'll take about a minute because it's going to retry that same one that fails a bunch of times just in case it can get a response out of it. But it will show the same results unless they fixed it, since I just announced it earlier today. Cool. We identified the lame delegation is not authoritative, and 1 million delegations. But you can provide this tool multiple domain names, or you can give it a list of as many domain names as you want. It was built to work at scale. All right. That's in case the demo didn't work. So let's take this a step further. Can we take over ShmooCon.org? Again, we know the 2 name servers for ShmooCon.org cresting our committees. We know the first one works. Crusty works, it resolves appropriately. Archimedes does not. It times out, so we know that there's no name server listing there. We can look up the IP addresses of both of these name servers. And if we say to do a whois on those net blocks, we see that they're owned by different networks. So the one that works is probably where ShmooCon currently hosts their DNS infrastructure. The other one is probably something I honestly actually have no idea, but it's an entirely unrelated network. It's not like 2 name servers in the same network. Whoever controls that net block could spin up a name server and start taking over probably half the queries for ShmooCon's website. I also briefly want a quick note on CCTLDs. CCTLDs are country code TLDs. They're 2 characters. They are generally not required to follow the same security practices and guidelines as normal TLDs, but most of them do anyways. As a related but different project, I spent a few years doing daily scans looking for lame delegations and many other problems in DNS at all TLDs. So looking for TLDs that you can potentially compromise with other lame delegations or other issues, and I actually found many. And some of which could result in a partial or full takeover of actual TLDs, which would also include all the domain names below them. One thing of note, all the issues found that I identified were exclusively in CCTLDs, likely because they don't have to follow all the best practices. I don't know that, but there's a good strong correlation there. I reported all the issues I found. Most of the TLD operators were very receptive and very thankful for my reports. However, a few were not. A few never responded, got back to me, and a few were even hostile, unfortunately. And that's one point that was something to consider when looking for a domain name for your next project. If you want to try to reduce the amount of potential security exposure, choosing one with a better track record might help. Not saying all CCTLs are bad, but some of them follow these best practices, some don't. And I want to do another quick demo. So I've shown how this works with, say, 1 domain. But what happens if we do a lot more? So domains.txt is a list of, that I have here, is a list of 1,000 random domain names I've done from my domain name database, because I literally have a database of every domain name on the internet. All of these are active this morning. I'm actually just going to make this run a little bit faster. It defaults to 10 threads. I'm going to give it 40, so it's 1,000. And as you see, it's already finding lame delegations. These are literally just random domain names that are active in the zone files right now. This will take probably, these 1,000 domain names on 40 threads will probably take about 5 minutes, but I also ran this like an hour ago. And you can see of the, I guess I have 1,003 domains in there, it found 191 lame delegations and 196 other problems. Those other problems could be things that aren't really, couldn't lead to compromise, but they might be something a DNS operator might want to fix, such as two authoritative name servers getting back different results. So this, actually, this only took like a minute and 20 seconds to run when I last ran this. Actually, the more domain names you add to this, the more effective you actually recache the same result on each invocation. Back over there. The code is here, and the parent project is under DNS Coffee. That's all. I guess I can have a few extra minutes if anyone has any questions. All right, thank you.